All right. Good evening, good morning, good afternoon, whatever time it may be where you are. Welcome to the late night MAST summer webinar. I'm Thomas Tukevich. I am the technical writer for the MAST archive. And if you haven't met me yet, I am the one running these webinar sessions. So welcome. Thank you for joining us. If you haven't already logged into the platform here, you should follow this link and get signed in so that you can get your instance up and running. Once you do, you'll be dropped into not this directory. You'll likely be dropped into this content directory in the type content reference directory. So once you're there, you can navigate through notebooks, webinar series. I have two of these in here, but you'll have just one that has that's the correct name, Asteroseismology, and then you'll find these two notebooks in there. If you haven't done one of the webinars before, the live version is what I use. It is totally blank, and I code along. I fill in all of the blank spaces and put the code in there. If you want to code along with me, feel free to do the live version. If you just want to see the answers so you can process what's going on and anticipate what I'm going to say, that's also fine. Or you can also just watch the webinar. You don't even have to interact, but just so you understand the difference between those two things. Welcome to lesson, well, it depends on whether we're Python indexing or not. This is lesson 2 if we're Python indexing, or lesson 3 if we're counting like normal human beings prefer to do. But at any rate, today's lesson is going to be on asteroseismology and other spurious signals. This is a bit tongue-in-cheek, as there are plenty of interesting, scientifically valid things to study in TESS data and in light curves. The goal for this lesson is to understand some of those things. So you should be able to list a couple of the non-planetary sources of periodic signals in a light curve, and we'll talk about binary and variable stars. You'll also learn how to subtract a non-planetary signal from a periodogram to reveal the signal of a transiting exoplanet. And you'll also list possible sources of false transits. So we'll talk very briefly about reasons why you might get the wrong answer when you're searching for the origin of a signal in your data. To that end, I'll give us just a little bit of background on some of these topics, and then we will dive right into doing the analysis. So to start with, the introduction into exoplanets. We did a lesson on this one last time, so if you haven't already seen the recording, or if you weren't able to do it last time, you should definitely go back and watch that recording. But exoplanet science is very exciting. There are a lot of very brilliant people working on this, and there's sort of almost a new discovery every day. Part of this success is that we have the transit method, which has turned out to be very, very successful for detecting exoplanets. And we look for periodic dimming in the brightness of stars, and that lets us know that a planet has passed between us and the host star relative to our line of sight. So it's blocked some of that light as it passed in front of the planet. But there are other things that cause repeated dips in brightness of stars, and we should probably be aware of those before we go declaring that we have found the next Earth. And so we're going to take a look at one particular thing that might cause some confusion when you are analyzing these light curves. This notebook will assume a little bit of familiarity with binary stars, exoplanets, and light curves. So again, there's previous recordings. There's also links here. And I do encourage you to check these things out if or after the webinar if you are not already familiar with them. Let's talk a little bit more specifically about why a binary system light curve might look similar to an exoplanet transit. And we've got two side-by-side diagrams here to sort of drive this point home, or help to understand why it is that these two things might be confused for each other. So on the right is our standard light curve of an exoplanet transit. Once the planet passes in front of its host star, we get this characteristic transit dimming shape. Now, the thing is, we also get that same shape if a star passes in front of another star and blocks some of its light. And again, I just do want to emphasize how very similar these are, even at the more fine-grained level. You get these sloping sides, you get this sort of smooth, curved bottom part of the transit, and then you get another sloping side. And that will be identical when you're looking at two stars that are orbiting about a common center of mass. The key difference between these two is that there are really two distinct transits or eclipses in the binary star system. Stars are not going to be exactly the same size, so there's generally some variation in the depths of transits and in the relative drop in brightness, and that's just due to whether it's the primary eclipse, so when the smaller star is eclipsing the larger one, or the other way around, the secondary eclipse when the larger star is covering up the smaller one. And so this distinction between an exoplanet transit, which has these regular, repeated, same depth transits, and a binary star system, which has slightly subtly different ones, is kind of the key distinguishing factor between the two of them. Now, you can imagine this might get really tricky if you had two stars that were of very similar mass. Your light curve might end up looking very, very similar to an exoplanet transit. But fortunately, you can still usually distinguish between them. They're not usually perfectly identical. But that's kind of the physical origin of why these two things might look similar, and why we need to be careful when we're analyzing these things. Also, hint, hint, keep this topic in the back of your brain because we are going to use it later in this notebook. All right, that's the background out of the way. Now we can dive into the code part, which I know is the thing everybody's excited for. We've got our import statements as usual. The packages of note, astroquery.mast, still going to use that to query for observations. S3FS, still going to use that to access cloud data. Lightcurve is something new, though. Lightcurve is a wonderful package. We're going to talk about it a little bit in detail later, but we're going to use it to analyze light curves. Suffice it to say that that's what we'll do, and the details will come after. Now, let's start our query. Let's start diving into this analysis by searching for a target. So the target that we're going to use is this V839 SEP, which is a known binary star system. So we already know we're going to get an interesting light curve. To speed up our query a bit, what we'll do is we'll say that obs equals observations dot query, query underscore criteria. If you have not seen me do this before, please hit tab when you are typing the names of functions. Jupyter will autocomplete for you. Don't spend years using this platform not knowing that like I did. Hit tab to autocomplete and save yourself the pain. Anyway, the first thing we're going to do to speed this up a bit is we'll say that target name equals, and this is a doozy to type, 3754222201. This is just the tick ID for this particular target, and searching on this is going to be faster than trying to resolve the actual name. We'll set obs collection, aka mission, equal to TESS. We'll set data product type equal to time series. And we will set sequence number, aka sector, in the case of TESS, equal to 15, 16, and 17. We're restricting our sectors here for two reasons. One, as always, to kind of limit the scope of the results we get back so it's easier for us to understand and talk about, but also more in a more scientifically typical way. 15, 16, and 17 are back-to-back-to-back sectors, which makes it easier for us to create a combined light curve without having to worry about other effects or considering the fact that a year might have elapsed between observations. So this picking these three is done for the purpose of consistency. All right, so we've set up the observations query. Now let's say that we've got our data products, which are observations.get product list, pass in the observations, filtered products, is observations dot filter products. Oops, I can spell it right. Filter products. Pass in the data products. But I haven't applied the filter. Description is light curves. And then we'll take our filtered products and use that to generate cloud URIs using observations dot get cloud URIs. We'll pass in filtered products. And we'll take a look at what that's generated for us. Data products is not defined because it's just data prod. I think after typing that 3 times today, I would get it right, but here we are. We've gotten back our 3 cloud URIs, just as a quick check to make sure that this looks okay. I see a sector 15, 16, 17. It's got the sectors, and I also see that it's the light curve files here. So it looks like this is a sensible result. This is more or less what we were expecting to get back. Okay, this is pretty standard. If this isn't familiar, if you're just joining us, please do go back and watch the lesson 0, lesson 1 recordings, because we go into more detail about how you would perform this query and how you do searches and just generally get access to the data that's in MAST. So if that felt really fast, definitely go back and watch those recordings. Since we have our cloud URIs, though, we can actually get started using the light curve package, and here's where I'm going to talk about how great light curve is. It's a pretty wonderful open source tool. It's new to us. We haven't used it before in this, but it was specifically designed for use with Kepler, with data from the Kepler mission and from the TESS mission. And there are a ton of handy features. So the 3 that we're going to use a lot today are the automatic flux normalized stitching. So what that means is if you take data from multiple sectors and you give it to light curve will automatically normalize them by the median and then make sure that they all line up with each other. So it'll make sure that that when the stitching is done, there's no big gaps in the data. And this might happen because in between sectors, TESS has to stop pointing at that part of the sky that it was looking at and then turn itself so that it can transmit that data back to Earth. And that means that because it's changed its position back and forth on the sky, the sun might be hitting it at a different spot, and there might be thermal effects on the detectors. And then when it points back at that part of the sky, it might not be rotated the same way. So it's possible that there's a bit more stray light in one spot, or the position of the moon might have changed. There's just a million things. There's just a million reasons why that flux value could be different between sectors. And so light curve kind of takes the load off and make sure that when you stitch these together into a bigger light curve, you make one light curve out of multiple smaller ones, that it will make sense and things will line up. You do have to be careful when using this because there might be cases where something is actually varying and you're removing information from it. You can imagine if you were looking at a star for long periods of time, say half a year, if a star had a period of half a year and you said, oh, well, TESS has observed this for half a year. Well, TESS has observed it in discrete 27-day segments. And if you flatten all of those in 27-day chunks, you might actually flatten the signal out of your analysis. So it's very handy in most cases, but that's just a caveat to put out there. You can't use it for every application. Okay, that's enough about stitching, but the other 2 features we'll use are phase folded plotting, which is super useful, and we'll talk about what makes it so great in the notebook. And then also the fact that there's built-in Fourier transforms that create periodograms for you that you can use to determine orbital periods. We will also talk about this further. There is a link to a 3 blue, 1 brown video here about Fourier transforms. He does it far more justice than I ever could, and the animations are just spectacular. So if that's not a concept you've worked with before, I do highly recommend that you check that one out. Okay, let's get get loading things into Lightcurve. The syntax might look a little awkward, and it's just because Lightcurve is a great tool, but it doesn't quite fully integrate with cloud things yet, or that's not built into its functionality, so we do have to kind of do things in a bit of a clunky way. We'll start with a very familiar syntax with fs.open, CURIs, the 0th one. We'll read that in as a binary, and we'll call it f. Next, we'll do with fits.open, pass in f in read-only mode as FTS for fits. Now what we'll do is we'll say LC1, so this is my Lightcurve 1, is LK, that's the Lightcurve with a K open source package, dot TESS, TESS, let's type a little more, TESS Lightcurve. We're going to do TESS Lightcurve file, and we'll pass in this fits.open object that we just did. And this will just basically read in this file and create a Lightcurve object for us. And that comes with lots of nice functionality. And as an example of that, we can create a plot with this lc1.plot. So again, it's added this dot plot functionality to this object. When I run this, we'll get a pretty phenomenal looking plot. Actually, it's already got the labels for flux. It already talks about the time on the x-axis, and it even appropriately labels it. The TESS mission uses this barycentric TESS Julian date, which is corrected to the date of spacecraft launch. And I always forget this acronym when I'm making a graph like this, and so it's nice that Lightcurve just throws it on there for you. Also, just as a quick check to make sure that this makes sense, we can see that there's around 27 days of data, right? From 1715 to 1735 is 20, and I see a couple extra on the end, so that's about 27. So we know we plotted the first sector. Good, great. We've opened the first one. At this point, you can also probably see that there are some characteristic features of the systems that we talked about. Already we're seeing two separate transits of different depths, which is sort of the hallmark of a binary, a transiting binary system. I will also say there's interesting things happening up at the top here too. It looks like there are maybe additional flux drops of some kind that are occurring, and then there's also some sort of repeating pattern up at the top. We'll talk a little bit about that at the end of the notebook, but for now we'll focus on these larger transits. Before we do any of that, though, we need to open up the rest of the data. Since the syntax, we type it a lot, I've left this one mostly filled in. The only thing that we have to do is loop through the remaining light curves and stitch them together. So we'll do a for LC in C cloud URIs, starting with the first one, because we've already, starting with the one at index 1, because we've already done the one at index 0. We continue past that to get all the remaining cloud URIs. So this will go through that loop. It will open up all the files. Once it does, we need to load them into Lightcurve. So our new LC equals lightcurve.tess Lightcurve file. Same thing that we did up above. Only now we're going to add it to LC1. The way we'll do that is slightly clunky. We're going to do lk.lightCurve collection. Notice that I typed double parentheses, and that's important. So double parentheses LC1, comma, new LC. Close those double parentheses, and then we'll do a dot stitch, and I'll explain why I just did that. What the Lightcurve collection is doing for us, it's actually a very aptly named object. The Lightcurve collection is a collection of light curves. It's a container that you can put light curves inside of, and it will hold multiple of them. The reason why you might put multiple of them into the container is that you then have access to this dot stitch function. And the stitch function, we've already talked about that. We know what it does. It's going to normalize them so that we can look at a target star over multiple sectors and be comparing apples to apples and not have to worry about thermal effects, scattered light, all this other stuff. So by setting it up this way, we'll loop through all the other ones and we'll just end up putting them into this collection and then doing this dot stitch, which will take it from a collection of light curves into one slightly longer light curve. So one sector at a time, we'll add things on. Once this loop has finished, we'll be able to do lc1.plot again, because we'll be back to a light curve. So if we run this, indeed, we get a much larger plot, or a plot that extends is more extensive in time. And the patterns that we noticed in the previous sector still hold true when we add more data. That's good news. Something interesting is definitely happening in our star system. There really was no doubt from the first graph, but now we have a lot more data to prove it, and we can probably do a little bit of a better analysis as a result. Okay. To actually do our analysis, we're going to create a periodogram. As I said before, periodogram relies on Fourier transforms. I put the link here again to the 3 blue 1 brown video. It's really excellent if you don't work with this regularly, or if you just, honestly, even if you work with this all the time, watch the video. It's really good. He does an excellent job explaining it, and I feel like it helps to develop an intuition for it that I certainly didn't have when I first learned about Fourier transforms. If you're not familiar, the quick summary is that it'll take a Fourier transform, will take our signal and turn it into its associated frequencies and their relative strengths. And that's exactly what we want to know, right? We want to figure out what the characteristic period of this system is. In light curves implementation, we'll specify a range of frequencies to check in days. And we'll also have to specify a method for computing the transformation. And in this case, it's actually going to be a box least square method. And so this is our way of modeling the transit. The couple of key features are, first of all, the reference time. And you can sort of think of this as the starting point. We need some way to say, well, where does a periodic oscillation begin? And for the purposes of this model, it's right at the center of the trough or lowest point of the transit. The other key features are duration, how long does the transit last, period, how long between transits, and then also depth, which is just the fraction of light that gets blocked when the object passes in front of the star. We'll use period, duration, and reference time later in the calculations. Depth is often relevant in other types of calculations, like determining stellar properties, but we won't be using that one today. And I just do want to underscore, this seems like this model is really bad, and surely it couldn't work. It's just a whole bunch of boxes. But actually, it does a very excellent job under these conditions and under most conditions where you would be looking for this type of repeated change in brightness behavior. It actually does just fine. It'll pick out the signal without really much difficulty at all. So let's actually run it. That's enough talking about what it is and how it works. Let's actually create one of these. To do that, we have to set up a period grid over which we're going to check. So we'll say period equals np dot inspace from 1 to 20 with 10,000 steps. So again, just to emphasize that we'll start at 1, and we'll go up to 20, and it will do that in 10,000 steps. So it'll give us a whole bunch of increments to test over. This is not really how we should do this. There are ways to set the upper and lower limits for these periods, or strictly speaking, for these frequencies, based on the Nyquist sampling theorem. But you can think about one end of it as you wouldn't try to claim that you had detected something that had a 75-day period after only 25 days of observations. You just wouldn't have enough data to support that conclusion. And in fact, ideally, you would have at least 2 data points just to make sure that something didn't go wrong in the measurement. And especially when you're talking about a transit and you want to declare that you found a planet. You definitely want to see it at least twice. So that would constrain your ability to set upper and lower limits on the period. At any rate, this is the space that we're going to use. It works fine for this example, and we'll plug it into our analysis here. We'll set that up with BLS, box least squares, the method we're using above, and we will call LC1 dot, so this is another light curve magic thing. We'll use the 2 periodogram. So it's going to take all of the data that we already have in the light curve, and it's going to run it through this periodogram analysis. We need to tell it that the method is box least squares, and that the period grid to use is the period grid that we just created in the line before. We'll also do BLS.plot. And if you're curious why I added semicolons to both of those lines, it's because it will suppress some output that we really don't need to print when we do these things. We'll also save one of the likely parameters, and in this case, it's actually going to be the binary period. So that's going to be BLS.period at max power. And we'll print that out so we can take a look at it. And you'll see what that means pretty clearly once this runs and we get the plot back. Also, and before I could even finish saying that this was the most computationally intensive cell in the whole notebook, it already finished running. So this Fourier transform was the most complicated thing for the computer to do, and it does actually run rather quickly, even in the platform. But at any rate, we've got our periodogram back. We've got our period at maximum power, which is 4.98 days. And now let's talk a little bit about how to interpret this. So you can see that the largest spike in our graph occurs right here at what I'm going to call, for convenience, 5 days. The way that we can interpret this is by thinking about the BLS power as the strength of the associated period. Normally, these Fourier transformations are done in the frequency space, but it's often a lot more natural when we're thinking about exoplanets or binary star systems to talk about it in the period space. I personally can't, even though it's just a 1/over transformation, I personally can't do that while looking at a graph, and it's kind of mind melting. And so the default in light curve is actually to show you it as plotted over a period. The other things that we might want to notice, in addition to knowing that the strength of this peak tells you the relative strength of that frequency, is that there are a lot of peaks here, and surely these can't all be real. And in fact, you may notice that a lot of them are harmonics, or they've been aliased. So in this case, if we say that our maximum peak is at 5, you can see that there's also one at 10, double this period. There's also one at half, at 2.5. And so you get these aliases of a true period in your periodogram. To make sure that you found the right value, what we can do is create a phase-folded light curve. So I alluded to this earlier, but a phase-folded light curve is basically a way to plot it to check this for consistency. And the way that you would go about this is by starting with your light curve, and I'm going to scroll back up to our light curve. You can imagine going along, plotting this data as normal. So you go through, you plot this first bigger spike, you plot the second smaller spike. And when you get to this spike, the larger dip again, you roll back to the beginning and you start plotting again from the left side of the plot. And by doing that, you would expect, if you've gotten the period right, that the largest transit would overlap itself. Again, if and only if you got the period right, you would expect that to overlap itself. And that's what makes this really useful, is that by folding things, it creates a very fast visual intuition for, have I gotten this right, yes or no? There is also a resource there. I know I've explained that rather quickly. So there is a resource here about creating a phase-folded light curve. It was put out by the Zooniverse open source collaboration, and it is an excellent video. So if you're a little bit If you are curious and want to hear a little bit more detail about how that gets generated, you can certainly look at that. So let's do that. Let's create a folded light curve right now and see how well that matches up with our values. So lc1.fold, the period is the binary period, and we will do a dot scatter. This is a new one. We're not doing dot plot because it doesn't really make sense for us to have a smooth connected line when we're folding the light curve on itself multiple times. A scatter, just plotting the points, makes a lot more sense. So let's do that. And oh no! Oh man, this isn't good. This clearly we've done something wrong. The period can't be right because we were just talking about how the whole point of this method is to show two separate, distinct transits that shouldn't overlap each other. We should only be wrapping around the light curve once we've gone through a whole cycle of flux variations. Clearly, that is not what is going on here. So ignoring, I know it's very cool. There's a lot of cool stuff at the top, but we're just ignoring that for now. Ignoring all of this happening here, you can see that the deeper transit is definitely visible. The shallower transit is also visible, but they're kind of layered on top of each other. So something has gone wrong with our calculation. And that brings us to the exercise. What is the real period? If we had picked the right value, this is not what we would see. We would see two separate transits. Thinking about the orbits of binary stars. And again, I want to remind you that at the beginning of this, there is this diagram talking about the light curve of a binary system and giving you some insights into the geometry. Thinking about that geometry, thinking about that type of system, what might be wrong with our calculated period? And if you can figure out what might be wrong with our calculated period, can you find the right period and use that to create a new phase-folded light curve? So it's just about 4 minutes past the hour. So I'm going to give everyone 5 minutes to work through this. So we'll call that 9 minutes past the hour. If you have any questions, please feel free to put stuff in the chat. I'll probably put a hint on the screen about a minute before time is up. Okay, I will stop talking so that everybody has time to work. Good luck, and we will check in soon. I see I only have one hand up, so this is my quick hint to everybody in the room. The answer has the form of this expression. And so the answer here, actually, if I substitute out these question marks, is 2. And when I fold this on what I've called the true period and make a quick scatter plot of it, you'll see what it looks like. So this is what we were expecting to see. Two very well separated transits of differing depths. They've all overlapped on each other. So this is probably the right period for our system. Now, the reason why I was so insistent about going back up to the top and looking at the geometry of the system and sort of thinking about it from that first principle is that the reason for this factor of 2 basically comes from the fact that the periodogram is not distinguishing very well between these two transits of differing depths. So what's happening is that when star A passes in front of star B along the line of sight, that is our shallow transit, let's say. Then it moves, both stars move about their common center of orbit, and then star B passes in front of star A. We've got the second transit. And so the periodogram says, aha, okay, transit, I found the period, it's complete. But that's not really what's happening, right? Because star A has only gone halfway around. Likewise with star B. They've each only traveled halfway around their full orbit. And so, in fact, the period that we're getting is too small by a factor of 2. We need to double it so that the stars go all the way back around to their original positions. And this is actually something that's very common when you're looking for this type of behavior, having like a degeneracy or something where the multiple a multiple, an integer multiple of the value is actually the real answer is exceptionally common in this type of situation. It's just because of the nature of what we're doing, especially with folded light curves. And this is still a very helpful way to diagnose things, but at times it can be frustrating when you're trying to figure out, well, what is this special magic factor that will actually get me to the correct answer? All right, so we found the stellar transits, and I want to make sure that we get through this next section. So I will keep us moving along here. Um, to start with, if we wanted to get rid of these, right, maybe we want to investigate this signal up at top. To mask out these stellar transits, your first idea might be something like, well, let's say that I create a spot where things are transiting, which is where the flux in this light curve is less than 0.94. And then let's take that light curve, only show the part where it's transiting, and turn that into a scatter plot. Okay, well, that's pretty compelling. Those certainly look like I've got the transits, but this really isn't going to work. There's still a bit of the transit that's between 0.94 and 1 that's going to contribute to the periodogram, because if we leave that out, there will still be this little part of our light curve, again, between this 0.94 and 1, that's going to weigh these values down here. So it's going to mess up our period calculation, probably significantly. What we can do instead is try to come up with a little bit of a better model for this transit, and indeed, light curve offers a pretty easy way for us to do that. Before we do, though, we need to know some of the characteristics of this pattern. So namely, when does the pattern start? How long does when does the pattern start? When do the transits start? What is the duration of the transit? So that we can come up with a model. What we'll do, it's just a little bit easier to work with these values as arrays. So we'll say that fluxes are lc1.flux.value. Again, we just want the numbers in this array. We don't want all of the extra stuff that comes with it. So that's why I'm doing the dot value. We'll say that time series is lc1 dot time singular dot value. Then, to identify the location of the transits, we're going to do transits is time series indexed at NP where fluxes are less than 0.95. Now, if you're thinking to yourself, hey, wait a minute, we just did that up above. Yes, we did. Yes, we did. But we're going to take it a little bit further this time. We can use the way that we've set things up now to identify when the very first transit is, or really what we're doing is we'll be able to collect all of these points at once by specifying a couple of things. And by collecting the whole transit, or at least this section of the transit, we should be able to estimate where the midpoint is, or where the deepest point of the transit is. And we'll also be able to estimate the duration with some level of accuracy. So the first or deeper transit is transits where transits are less than 1712. So I'm cheating a bit here. I'm looking at this graph and saying, well, I know 1712 is here, and that should just about clip all of this transit data into the section we want. It should be able to clip everything. Likewise, for the second one, we can see it's somewhere between 1716 and 1718. So we're gonna clip that one as well. So second is transits where transits less than 1718, but more than 1716. Oh, there's an underscore. Don't forget the underscore. Oh man, three times today. Oh, you can't. Okay, it's a great lesson for everyone. So let's talk about it. Too many indices. I've specified two different indices on a one-dimensional array, and that just doesn't work. That just doesn't make sense. So the computer rightly objects to my nonsense. What we need to do is add the np.bitwise, and which will combine these two indices into one singular one-dimensional index that Python can parse easily. Bitwise and okay, there we go. So what this has done is pulled out the first and second transit. Now we can calculate the mean time. So we'll do t time 1 is NP mean of the first. Again, just by taking the average of all the points, all the times in that first transit, we should be able to get the exact center of it. And then we'll do lowercase t, duration 1 is, what we're going to do is, since we've got that transit, we're going to take the point all the way at one end and the point all the way at the other end and figure out what the time difference is between them. So in the first transit, that means we're going to take the last point and subtract the first point. And then we'll do the same thing in the second transit. So t time 2 is NP mean second. And t duration 2 is the second, the last point of the second transit, minus, should have come up with different names for these, minus the first point of the second transit. Great. So we've got estimates for the time of transit and then the transit duration as well for both of these transits. And what we can do now is we can ask light curve to create a transit mask. This will mark all of those locations for us, so it will be easy for us to pull everything out. The one thing that we have to keep in mind is that our duration estimates are an underestimate, right? Like there's still a little bit of this this transit that we haven't captured. So what we'll do for this first one is we're going to say that our estimate is really bad. It's off by a factor of 10, which it probably is. That's actually a little bit absurd, but we're going to put that in anyway. It's not going to make too much of a difference, and in fact, it's better to err on the side of cleaning too much than cleaning too little. But we'll demonstrate just exactly what it does. So we'll set up the first mask as LC1 dot create transit mask. We need to pass in the transit time, which is t time 1. We need to pass in the period, which is the true period, and we need to pass in the duration, which is t duration 1 times 10. Again, that's kind of an absurd estimate, but let's just plot it and see what happens. We'll make a plot of just the mask, that is just the transits, and then we'll make a plot of everything but the mask. So this little tilde here means please do not on the mask I've just given you. Please make all the trues falses and all the falses true, so we'll get exactly the inverse. And it's just helpful to see what we're excluding and what we are keeping. Yeah, it definitely looks like we've removed some signal here. I'm seeing signal pretty clearly around several of our transits. So we've been a little bit too intense with our cleaning up, but it seems like it's okay. There's still enough data here, including the other transits, the slightly shallower transits. So now let's do a second mask. We're going to rinse, repeat. We're going to try to filter out those other transits. So we'll say that our second mask is LC1 dot create transit mask, just like we did before. This time, transit time is t time 2. The period, still the true period of the system. And the duration, please spell it right this time. Okay, duration is t duration 2 times, or let's say 3. 10 was kind of big. Let's try 3. That probably will get enough. And we'll do the same thing. We'll create plots of both of them, both the mask and the anti-mask. And this looks reasonable, right? We're still clipping a little bit of signal out on the side. Maybe it could be less than 3. But again, it's probably better to clip out too much data than not enough, because if we accidentally leave some of this in, it'll just dominate the resulting periodogram. And here's the cleaned flux now with the larger transits in place. So we've been able to separately clean out either of these transits, but we need to clean out the two of them together. Since we want to remove data anywhere there's a mask, we're going to need to use a bitwise OR, because in this case we want, if it's true that there's a mask in one place and false that there's a mask in the other, that's it doesn't really matter, right? We want it, either of those cases will trigger this this final mask if we want to remove them both. So what we'll call this is our combined transit mask, and we'll do an NP bitwise OR between mask 1 and mask 2. And we can quickly create a plot that has all of the transits removed. Now, if you're looking at this and going, wait a minute, I still see transits, what did we miss? Well, actually, now that we've removed the big ones, these smaller ones become a lot more obvious. And also you see a lot more of this squiggly signal, let's call it, coming from this star. We'll look for additional signals. We're just going to actually rinse and repeat what we've done before. So we're going to take this brand new cleaned up light curve and we're going to pass it through a periodogram. So our box least squares is this no binary thing is this light curve with the binary transits stripped out of it. That's what got saved here when we used our transit mask. So we'll do no binary dots to periodogram. Again, method is BLS. Period is the periods that we just set up above, and we will run that. We get back a new periodogram with a maximum peak at 4.7 days. We want to double check that this is the right thing. I'll start typing that. So this is still our no binary light curve. We'll do dot fold. Period is the new period, and that's this 4.07 days. That's what got saved. It's the new period. The epoch time, so we're looking at when the very first one of these transits started. Just to center things a little bit better in our plot. And while that's running, I'll scroll back up. You could basically, so what all I did was I looked at where this first transit fell and I said, well, okay, that's roughly 17, so this is 1710. Well, it must be somewhere around 1713. And then I just adjusted until I got one that got us close enough. And you can see it's beautifully, right? It's beautifully centered in the middle there. This very clearly looks like a transit. And also there's some very fun spaghetti strand patterns going on up above. And that really is the actual asteroseismology. So just because you see periodic dips in brightness doesn't necessarily mean that you have identified a planet. In this case, there's a very clear transit signal, but a sinusoid alone is not enough. Plenty of things can cause that, from star spots and stellar rotation to the actual expansion and contraction of the star itself. There's many, many things it could be. I also want to leave you on the note that even though this graph highly suggests that this is a transit, nobody has actually followed up on this. So this was reported in this paper, which is part of the Zooniverse collaboration. So citizen scientists who spend time identifying these patterns, and it is identified as a candidate multiple system 4 years ago, but nobody has actually followed up with another telescope to see what's going on here or what the properties of this planet might be. And I just thought that would be interesting for this notebook, instead of saying, here is established fact and we're just kind of recreating it. No, there's actually still plenty of things out here that haven't been confirmed or need to be followed up on, or just haven't gotten the full attention that they need. So there's still plenty of exploring to be done in the MAST archive. For the curious, you could try to strip out this transit model, and then you could analyze this actual pattern available in the star, but we're going to leave that as an exercise for the reader. Next time on MAST Summer Webinar, so that's all the content for this lesson today. Next time on MAST Summer Webinar, we're going to look at transient phenomena that get observed by TESS. So everybody get ready to hunt for supernovae. I think that one's going to be really fun. This lesson is I think one of my favorites.